Hi viewers, welcome to my class on mechanics of materials. In today's class, we'll derive the relationship between bending moment, shear force and rate of loading. To establish the relationship between bending moment, shear force and rate of loading, let us consider a portion of a beam subjected to distributed load. Let us take a small differential portion of the beam subjected to distributed load. This is a beam subjected to distributed load. I am taking a very small element, a small portion of the beam subjected to this distributed load. So this is a differential element, and this differential element is shown here. So it is subjected to distributed load. Since it is a very small length, differential length, this variation of this distributed load can be neglected, and we will take that load intensity as W. So the intensity of load is W, and the resultant load acting is W dx. W is the intensity. W is the intensity in kilonewton per meter or Newton per meter into length. This small elemental length, that is dx, will give the resultant load. So resultant load is W dx, and it will act at the center, that is at a distance dx by 2. Now the element is in equilibrium under the action of the force transmitted from this left part. The force is transmitted from the left part and force is transmitted from the right part. So when you remove this portion, and to obtain the equilibrium, the force acting on that part plus the forces transmitted to that part from this portion and forces transmitted to that element from the right portion has to be shown. So force transmitted from left side is shear force and bending moment. Shear force and bending moment. And from right side there is a again shear force and bending moment. Now in this differential element, the variation of shear force is taken as dV. So there is a small change in shear force as you move from one end of the element to the other end of the element. From left end of the element to the right end of the element, when you move, there is a small change in shear force, and that is given by dV. So left side the shear force is V, and right side is V plus dV. Similarly, bending moment also there is a small variation. M is the bending moment at the left end of the element, and the bending moment has changed from M to M plus dm. This change can be either plus or minus. Dm can be positive or negative. Similarly, dV can be positive or negative. So under the action of these forces and moment, the element is in equilibrium. Now let us take the force summation. Since the element is in equilibrium, we can take the force summation and equate to 0. In this case, the forces are acting only in vertical direction, so you can take the force summation in the vertical direction and equate to 0. That is sigma Fy, you can equate to 0. So there you have force acting on the left face of this element, that is V, and resultant load acting, that is W dx, and V plus dV, that is a shear force on the right face of the element. So this is acting upward, this is downward, this is downward. So this can be taken as plus, minus, minus. So plus V minus V plus dV minus W dx is equal to 0. So that is the force summation in the vertical direction. So here V minus V cancels, you get minus dV minus W dx is equal to 0, or minus dV minus W dx is equal to 0. So if you rearrange, you will get dV by dx is equal to minus W. dV by dx is equal to minus W. This is a relationship between shear force and rate of loading. So this shows that the rate of change of shear force with respect to distance is equal to rate of loading. So minus of rate of loading. Now to get a relationship between bending moment and shear force, we'll take the moment summation with respect to the left face of that element. So this element subjected to distributed load of intensity W. Now let us take the moment summation with respect to left face. Say let us take it C with respect to C. So with respect to point C, if you take the moment summation, sigma mc is equal to 0. So this clockwise moment is plus m, and this is anti-clockwise moment minus m plus dm. So this moments, you need not consider the distance, directly you can sum up plus m minus m plus dm. Now this force is passing through that this phase, so the moment of this force is 0. So I have shown some distance, but it is acting on this phase. It is acting on this phase, so it is passing through point C. So the moment of V is 0. Now V plus dV is producing a clockwise moment, and the moment of that is V plus dV into dx. So it is producing a clockwise moment with respect to point C. So that moment is V plus dV into dx. V plus dV into dx. And this is also producing a clockwise moment with respect to C. And since the distance is dx by 2, W dx into dx by 2. W dx into dx by 2. That is the moment produced by this distributed load. So this is clockwise moment, so plus. So this is a moment summation with respect to point C. Now when you expand this, m minus minus dm plus v dx plus dv dx plus w dx into dx square by 2 is equal to 0. Now here m cancels, you get minus dm plus v dx. Here you have dv dx and dx square. So this term dv dx, differential change in shear force into differential length. So this is a product of differential quantities. You can neglect this quantity will be very small, because differential change in shear force and differential length of the element, so it's small. And dx square, dx is very small, the differential length, and it's a square of the differential length, so this term will be small. Even after multiplying the w by 2, since the differential length is very small, these two terms can be neglected. So these two terms involves the product of differential quantities, so can be neglected, and you get only minus dm plus v dx is equal to 0. So neglecting the product of differential terms, you get minus dm plus v dx is equal to 0. Or rearranging, you get dm by dx is equal to v. So that means rate of change of bending moment with respect to distance is equal to shear force. So this is a relationship between bending moment and shear force. So we got the relationship between shear force and rate of loading, and bending moment and shear force. This relationship can be used while drawing the shear force and bending moment diagram. dV by dx is equal to minus w, that is we have obtained dV by dx is equal to minus w. So w stands for the rate of loading. So when there is no rate of loading, no distributed load on part of the beam, then that w will be 0, and you get dV by dx is equal to 0. So to get dV by dx 0, the rate of change of shear force 0. Rate of change of shear force 0 means shear force variation with respect to x should not be there. So that means the shear force diagram should be either constant or it should have a peak like this. So the slope should be 0 at that point. Suppose you take this section B to C, there is only point load acting at B and C, and there is no load between these two, and here you should have dV by dx 0. So when dV by dx is 0 for this entire length, there should not be any change in shear force with respect to the length L. So shear force should be constant for that. So dV by dx, there is no variation for shear force with respect to the distance x. So you get the shear force is constant for that section. Similarly here A to B and C to D also shear force should be constant. There should not be any variation. It has to be constant, and here also it should be constant. Here again it should be constant, either negative or positive. The shear force diagram should be horizontal. We already know that when point loads are acting, shear force is going to be constant between these point loads. So when there is no load between the points, shear force remains constant. And this relationship also established the same understanding. Hence, wherever rate of loading is 0, the shear force must be constant in this part of the beam. We have another relation, dm by dx is equal to V. Rate of change of bending moment is equal to shear force. Now, when shear force is 0, at any particular point shear force is 0, you get dm by dx is equal to 0. So that means rate of change of bending moment is equal to 0. So wherever you get 0 shear force, either at a point or for the entire length of the beam. Suppose you have shear force 0 for the some part of the beam length, and so for one entire section, that is B to C or A to B, shear force is 0. There, when shear force is 0 for a distance, then dm by dx is 0. Rate of change of bending moment will not exist there, then bending moment should be constant there. Similar to this relation, when rate of loading is 0 for the particular section, then shear force should be constant. Similar to that, if shear force is 0 for that entire section, then bending moment should be constant. Now also shear force can come to 0 at a particular point. At one particular point, if a shear force is 0, then there you should have dm by dx 0, or slope of the bending moment curve should be 0. Dm by dx, that means rate of change of bending moment with respect to distance, or slope of the bending moment curve, that should be 0. So corresponding to this point, which one particular point, if shear force is coming to 0, corresponding to that point, the slope of the bending moment curve should be 0, or bending moment curve should have a peak point. It need not be maximum, the peak can be minimum also, like it can have a peak like this. So bending moment curve can be like this, but always wherever shear force is 0, that should have a peak point. Okay, that can be maximum or minimum. So in this relation suggests that whenever shear force diagram, shear force comes to 0 at any point, there should have a peak point for the bending moment curve, and that point is going to be important for us when shear force is 0. Since we are having a peak for the bending moment, that point has to be marked in the bending moment diagram. So that's all for today. Thank you for watching.